In this video, we're going to define non-singular matrices, not by determinants, that's coming up later, but rather by the reduced row echelon form and what our solutions are based on that. So first, let's talk about what we're specifically looking at. We're looking at square matrices. When we say we have a square matrix, that means the number of rows and the number of columns are the same. So m by n. And I just want to stop and say that right now we're not necessarily working on systems of equations. We're more or less just working with matrices. And I might say this is a homogeneous system of equations. But for right now, we're just talking about matrices. And so we want to think about what we're doing is not necessarily a solution set. It's not necessarily a system of equations. It's just a square matrix or not a square matrix in which it is just an array of numbers right now. So if I'm asked to determine whether or not it's a square matrix, I have to make sure that I have the same number of rows as I have columns. Now, for my A matrix, my number of rows is 3, but my number of columns is 5. So clearly you can see it's not square. This is not a square matrix. Then on B, I have got 4 rows and 5 columns, so it is a square matrix. We're going to define non-singular matrices in terms of a square matrix. So suppose A is a square matrix. And suppose further that the solution to the homogeneous linear system of equations is the trivial solution. Then we say that A, the matrix A, is a non-singular matrix. Otherwise we say it's singular. Non-singular here means that we have a single solution, and that solution is the trivial solution. And you're thinking, what? That makes no sense. Why are we doing that? Well, if you can just hold on until we get to determinants later in the book, we will talk about why we call it a non-singular matrix in terms of the determinants. Now, so for right now, just remember that non-singular matrices means that the solution is a trivial solution if the matrix represents a homogeneous system of equations. Now, a couple of things to note is we can decide whether or not the singularity for any square matrix. And we can also talk about it in terms of a homogeneous equation. So when we're talking about a singularity, it is not necessarily a system of equations. It may just be a matrix. So if we look at our 2 or 3 examples here, and we are trying to determine if the matrix is singular or not, based on the definition in this chapter, this section, then first of all, we can't even talk about singular or non-singular unless it's square. So we take a look at our first example and we ask ourselves, is this square? And if the answer is yes, we continue to ask questions. So it's square. And looking at A, I ask myself, do I get the trivial solution? And the answer is no. So from previous sections that we talked about, the answer is no because of the fact that for it to be a trivial solution, I cannot have a row of zeros. If I have a row of zeros, then I know that my null for this matrix is not going to be the trivial. I'd actually solve this by saying, oh, I'm looking at, assuming that it was in row echelon, so I would have divided by -2 and all that stuff, all those shenanigans. But what I do know just by looking at it, even when I do the next step, which is to put it in reduced row echelon form, that for A, that I'm going to have the free variable will be the x sub 3. And the fact that I have a free variable says to me it is a non-trivial solution, which means this is a singular matrix. So if I take a look at B then, I ask myself, is this square? And yes, I have 4 rows, 4 columns. Then when I did the reduced row echelon form, so again, I asked myself, is it square? The answer is yes, so then I asked the next question. Is the solution the trivial solution? And the answer is yes. This is the trivial solution because I have all my pivots are in each column. There's no column without a pivot. So that means that my null space is the 0 vector. So this one is non-singular. Now let's take a look at my next example. My next example, I ask myself, is it square? We always ask that first. Is it a square matrix? And the answer is no, so I stop. So I'm not even going to talk about whether or not it's singular or non-singular because it's not even a square matrix. And the way we are defining a singular or non-singular in this section is based on whether or not it's a square matrix. So I just stop and I move on. We haven't talked about the identity matrix, so let's talk about that now. We're going to define the identity matrix. The identity matrix is a square matrix, and you may see it noted in some books as I sub n or I sub m. It doesn't really matter what the subscript is. What matters is that the square matrix and the diagonal is ones, and everywhere else above and below the diagonal are zeros. So as this example, I have this diagonal, which is all ones. Above the diagonal is zeros, and below the diagonal is zeros. So that is the identity matrix. And that brings us into the next theorem. The next theorem says non-singular matrices row reduce to the identity matrix. So first of all, is it square? If the answer is yes, then we look to see whether or not it has row reduced to a identity matrix or not. If the answer is yes, then we know that the matrix is non-singular. So this is square, it row reduced to I sub 4 because there are 4 rows, 4 columns, which tells us it is non-singular. Let's look at our next example here. Our next example is it square? Yep. Did it row reduce to the echelon I sub 3? And the answer is no. I did not row reduce to the identity matrix, a 3 by 3 identity matrix. So this means it is singular. Now, let's talk about this in terms of the null space. Suppose A is a square matrix. A is non-singular if and only if the null space of A is only the 0 vector. So if I take a look at my first matrix up here using that theorem, I know that each one of these pivots are the basic variables. So my solution set for that would be let me erase this. Let me just erase this. Give me a moment. My solution set for A would have been the x sub 1, x sub 2, x sub 3, x sub 4 is equal to 0, 0, 0, and 0. So my null space is the 0 vector. Now if I take a look at my second example here, my null space is not going to be the 0 vector. I have a pivot or a dependent, d sub 1, is in the first column. I have a pivot, or d sub 2, the basic variable, is in the second column. My free variable is in the third column. And so what I know is that because my r does not equal my n, now if you remember, r is the number of free variables, and n is the size. And this tells me that my null space, my null of, we'll call this B, the null of B is not going to be equal to the 0 vector. So I know that B is not a non-singular. That means that it is a singular matrix by that theorem. Now what that does then is it brings us to the next theorem, and it says, suppose A is a square matrix. A is a non-singular matrix if and only if the system, L, the linear system of the coefficient matrix and some B vector, which is the constants, has a unique solution for every choice in the constant vector B. Let me just put that There. Proof, of course, is in your viewing pleasure. What does it mean? It means no matter which vector that we use for constants, whether it's a homogeneous or non-homogeneous, that vector, the constant vector that we pair with the non-singular coefficient matrix, will always yield a solution, and that solution will be unique. So then this brings us to our first round of non-singular matrix equivalence. Suppose A, the matrix A, is a square matrix, and then these four things are equivalent. It is non-singular, which means it's going to row reduce to identity matrix, which means the null space will be the zero vector, which means that if A represents the coefficient matrix, regardless of what my B vector is, whether it is zeros or not, doesn't have to be homogeneous anymore, whether it is zero or not, it will produce a unique solution for any choice that we choose for the B vector. And you're thinking, well, I vaguely remember this from my pre-calc 1 about singular and non-singular, but didn't we say something about it with determinants? And the answer is yes, we did. And we will explore determinants further, but not until we get to that chapter. So right now what we're doing is we're kind of building a basis, not necessarily talking about solutions of linear systems. So that's it for this video.